dimension selection with independent components.
Thank you, Mike, and thanks to the organisers for this excellent conference, and especially thanks to you, since it's obviously that you're the brain behind all of this. It's a pleasure to be here again, and what I want to talk to you about today is some work which I've done with my Japanese collaborator Kanta Naito on dimension selections. So let me start with statistics as usual in the terminology of Art Owen. So we're thinking of a data matrix that has a large number of dimensions and a reasonable number of samples. We're not particularly concerned whether the dimension is bigger than n or the other way around, but we're concerned with having a large amount of data. I'm going to be using an old approach, principal components, to start thinking about the structure in the data. Of course, we've gone a long way since principal components, but principal components are still very useful. And just to give you a list, of course, not a complete list of methods that are useful for analyzing this sort of data. There's, of course, factor analysis, multidimensional scaling. All of these have been mentioned in the conference. There's also projection, pursuit, and independent component analysis. These are some new methods that look for projections in a quite different way. And more recently, there were two methods by Taylor and al. And by Frank Critchley and al., which look at different ways again and trying to maximize different criteria for getting into the structure of the data. So there's plenty there, and I'm sure I've forgotten some methods that people also use, but basically I was thinking of linear methods of getting projections of the data. So we're well equipped getting into the data. What we do need to think about, or what I want to think about with you this morning, is how far do we dig into the data? When do we stop? And of course, life isn't so bad. We've got a number of methods there as well. We got the NIES or scree plot. Classically, we got the normal hypothesis tests when you know that the data is Gaussian. A method that is currently used very frequently is what I just called 95% variance cutoff. And most of you who've worked with data will know that many people stop looking at the data and the number of components when they've reached about 95% of total variance. Some people in finance said to me, well, you know, sometimes we go to 97.5% because that's a little bit better, but basically we stop when we reach about that sort of number. And in fact, quite a bit of the work I've done with computer scientists in a medical area where we looked at data in emphysema, we stopped at that stage as well, because this is what we do, people told me, and this is where we stop. There's, of course, maximizing the maximum likelihood. That's an approach from around about 2000 by Tipping and Bishop, which also applies to normal data and works quite well for normal data, but doesn't seem to work quite so well when the data begins to be non-normal. And there's another approach. This is the one which I'm going to talk about, maximizing non-Gaussianity and finding a stopping point when we maximize that. I had to change my slides a little bit since coming here because people, of course, have moved on. And as we've heard whenever it was on Wednesday, I think, there is, of course, the BCV as well. So, maximizing non-Gaussianity. In 81, Huber said a projection is interesting if it has small entropy relative to other projections. Or, put it differently, the Gaussian distribution is the distribution that gives us the maximum entropy. Diaconis and Friedman, a little while later, said heuristically a projection is uninteresting if it is random or unstructured. A standard measure is entropy. Now, what does that mean? We're looking for structure in data. We're looking for directions in data. When we're looking for directions in data, in some sense, it doesn't matter whether the data is at the beginning of the direction point or way out. So to visualize in a very simplified way what interesting or not so interesting means, I've plotted a number of mixtures of Gaussians, and reduce them to the unit sphere. So in each case here in these three pictures, I've used 1, 2 and 3 Gaussians, a mixture of these, and then centered the data and reduced it to the unit sphere, or expanded it to the unit sphere. As we can see in the plot on the left, which is the mixture of one single Gaussian, so in other words, a normal model, there's no clear direction you would go into when you're looking for something interesting. I've colored them in different colors for the 2 and 3 components, but you can see the data is actually clustered. It almost looks a little bit like continents on the surface, and if you had to look for interesting directions, it is very clear what you would go for in this. Now obviously this isn't a proof, this is just a small visualization why normality might be not so interesting, or why non-normality might be more interesting to look for. Unfortunately, entropy, which is the ingredient that both Huber and Diaconis and Friedman and many others, of course, since then suggested we should use as a measure of non-Gaussianity, is not really feasible, especially when we go to higher dimensions, because entropy, to calculate the entropy, we do need to know the density of the data. And we can't estimate that, especially if we've got high dimensions and low sample size. So another criteria that statisticians have used, and have used for quite a while, to assess Gaussianity or non-Gaussianity is the skewness and kurtosis. The method I'm suggesting works for both. For simplicity, I will just talk about kurtosis, the fourth order moment, which I've defined here in the way I want to use it for multivariate data. So beta sub k, the k for 4 is the kurtosis, is the maximum over alpha, where the alphas come from a unit sphere in the appropriate dimension. There are a number of different definitions for multivariate kurtosis and skewness. This is the one I'm using, and I think it's reasonably well established, but there are other definitions around. Okay, we know most of that, modulo the fact that we don't have the population parameters, but we can replace them by the sample parameters. The quantity we have to estimate in the beta is the unit vector alpha, the direction vector alpha into which we want to project. And of course, these quantities have been around for a while, so we also know how to calculate it. In particular, there are two methods. One was suggested by Jones and Simpson in '87, which is the projection index, which gives us a way of calculating the alphas. And the other way is using independent component analysis, which also gives you as the source this vector alpha. I'm going to go for the second one, mainly because there is quite good computing which helps us do it. And that helps me do the work I actually want to do if I don't have to find all the computing myself. So we're going to use independent component analysis to find this direction vector alpha, which allows us to calculate the kurtosis for data. Now, for the moment, I will assume that my total data dimension is d, and I'm going to look at a fixed p, which is typically smaller. I'm going to start with the data, which is x. I'm going to center it. Then I use the usual principal component projections. This is the gamma, and I finally sphere the data, so it all has unit variance. These ZPs, which now live in p-dimensional space, I'm going to make the input to the kurtosis vector. So I'm going to calculate kurtosis in the top lines for the population, and I'm going to calculate the alpha naught, which is my direction vector for kurtosis, and I'm going to do that with ICA. Down here in red is the sample version, and this is sort of like a little red thread through my talk. This is the quantity I'm actually interested in, the sample version, beta k, and there must be a pointer somewhere. Thank you. Okay, so this is the quantity I'm interested in. I'm going to calculate it for p-dimensional space. I have n samples, and I don't care whether p or n is bigger at the moment. In fact, of course, we do know, because we're using principal component analysis, that p can't be bigger than n, because we can't actually go any further. So I'm going to calculate this kurtosis quantity, which is a scalar quantity, and I find that in terms of this direction vector alpha naught, which maximizes the quantity beta for the sample. In ICA, it turns out that this quantity is actually exactly the first independent component direction. So the question we haven't answered so far is, we know how to do it for one p, but which p are we actually going to use? Because this is exactly what we want to find out. Now, having got to the rate rate before, which we thought the n on k was this quantity here, it's natural to look at the bias of this quantity. So we're actually going to look for each dimension p. We're going to look at the bias of our sample, and we're looking at the actual quantity of interest, the population quantity, which is the beta. And the beta, in our case, as one always does, goes back to Gaussian. The beta is therefore comes from a multivariate Gaussian. Now, we can show that when we standardize our sample kurtosis correctly with n and the k is 4 for the kurtosis, that as n becomes large, this quantity here, the adjusted sample kurtosis, converges to the maximum of a zero mean Gaussian random field. We therefore also know that this works in distribution, therefore the expected value of my quantity of interest also converges to an expected value of a maximum of a zero mean Gaussian random field. So this sounds pretty good, so we're almost there. Unfortunately, it doesn't quite work out that simply, and we do need a little bit more work. The quantity, the expected value of this Gaussian random field, we can't actually estimate directly, and the best we can do is get an upper and lower bound for it. This is what the theorem here gives us. We get, for each fixed p, we get an upper and lower bound, and I'm not going to go into details how these quantities are calculated. They're a real mess. It turns out that the lower bound vanishes quite quickly with the dimension, so we don't need to worry too much about it. The upper bound looks quite simple with this expression. This is a chi-square, and this is a horrible sum. Unfortunately, we couldn't calculate that directly either, although it's explicitly given. MATLAB gave up, Mathematica gave up, C and Fortran didn't allow us to do it, so in the end we had to simulate the upper bound. But we can actually get the upper bound. So what we're going to do here is we're going to use the upper bound instead of this quantity, because we can't actually get hold of this quantity. So the upper bound will be our estimate for the expected value of the Gaussian field. And then finally, the way we choose our estimator for the dimension is we're looking at our rate thread again, this quantity of interest, and we're comparing that to the upper bound, again for the same p in each case. So we've got this quantity I hat of p, and then the actual selector will be the p, the dimension p, which maximizes the difference between our sample kurtosis and the Gaussian random field of the same dimension. So in a sense, what we're doing is we're looking for where is the largest deviation, in which dimension is the largest deviation between the Gaussian object of interest and the sample version. So we're maximizing the non-Gaussianity. We're looking for the dimension which maximizes the non-Gaussianity with this p. Of course, the method works, otherwise I wouldn't show it to you. We've done simulations, we've done looked at real data, but we'll leave that aside, because what I want to do now is move on to prediction very briefly and show you how we can apply this in prediction. So we have an x and a y. In our case, we allow the y to be multivariate as well. Y can either be regression responses or classification labels, makes no difference. The method varies slightly. So what we want to do is apply this dimension selection to the regression context. And the natural thing to do, of course, is to apply it directly to the x data. This is, however, causes us serious problems, because when we think about that, if we apply it directly to the x and choose our optimal dimension just based on the x data, there's no input from the response. And this can cause us to lose directions which are actually very important for prediction, because if they have small variance, PCA chooses completely by variance and they're gone. So it obviously, we cannot apply directly to the X data. Instead, we're applying variable ranking first, and a number of people have talked about variable ranking. In fact, Peter on Monday morning started with the third dot point here, the generalized correlation coefficient, which is a variable ranking that he's told us how he's doing. There are many other, well, there are a number of other variable rankings. The t-tests will know the correlation coefficient, which essentially looks at the marginals of the y data with the marginal of each of the x's. And finally, there's a method that we're using, which is a multivariate analog, or the multivariate generalization of the univariate correlation coefficient. And if you think about the definition of the correlation coefficient, this C matrix, which we know from canonical correlation analysis, is of course exactly a multivariate generalization of rho. Computationally, we're not using C directly because, as you of course know, sigma x to the minus a half we can't calculate directly when p is bigger than n, but formally we're using this in the actual algorithm. We're using a slightly different version. Okay, so here are some ranking methods. We tend to use the bottom one, but any of the ranking methods can be applied to what I'm going to say now. So the first step is we want to get the right dimension of the X data. So what we're going to do is we rank our subspace. So when we have our p-dimensional, d-dimensional subspace, we're going to rank the data by any of the ranking methods, and in order to avoid clutter on the algorithm, I haven't put the ordered brackets here as we normally do in statistics, but these are now the components ordered by whichever of the ranking algorithms you want to use. So we're going to go for the first m-dimensional subspace. We're going to use the first most important variables of the original space. And m, of course, goes up to the rank of the data. The rank of the data is R, and we tend to stop a little bit before because we don't actually want to use all the data. So for this xm subspace, we then look at p-dimensional subspaces of xm. In other words, we start with x2, x3, and so on. For these p-dimensional subspaces, we calculate our best direction, which is our alpha in the kurtosis. We then calculate the kurtosis value based on the p-dimensional subspace. And for each m, we then find finally the dimension h sub m, which is the best dimension in our m-dimensional subspace. So we're having a dual sequencing. We're looking at m. For fixed m, we generate the subspace, and we calculate the best dimension for this m-dimensional subspace. Exactly as before, and it now makes sense because we got the variables that are important for regression or prediction. The supervised prediction algorithm then finally is, this is our data in the normal regression formulation. We have our m-dimensional subspace, we get the dimension, and our prediction model then with a little bit of PCs involved there, but this time only with the dimension hm, then gives us the fitted model with some matrix which is q by h, and the data reduced up to hm dimensions. Generally, the way we find which m is best is by using either cross-validation or any other least error criterion. And to show you how it actually works in practice, here is one example. This is a quite large breast tumor survival data example with nearly 25,000 genes and 78 observations. One of the reasons we like this example is because it has survival times. Not only classification labels, but it actually has times to metastasis in this case, which are given in months. The table here shows you a couple of different versions we've used to calculate the best m and the best h. The first to refer to two versions of the ranking we've used, Koch-Naito, the ranking with B1 and the ranking with B2. This is just the one-dimensional correlation coefficient, but then calculated the M and H as we've just discussed. And finally, we compare that to a much simpler and faster version, which is also based on the correlation coefficient, but then just uses the first principal component direction, as we would typically do. As you can see, we're going down from 24,000 genes quite quickly. M is 50 here, and the final dimension is 11, 40, and 12. And here a little bit higher, and of course in this case we're stuck with 20 because we're only using the first direction, so we can't apply the algorithm. And here is the final data set. The red curve is our B1 method, the blue curve is the other method with our ranking algorithms. The solid black curve is using PC1 only. You can see there's quite a bit of improvement. Along the x-axis is the dimension, and the performance is on the y-axis. Thank you. Thanks.